Now I can start the screen. So this is Crepey screen that's capturing everything here. So this is what it will look like. It's not going to be my talking head, just my talking voice. But this is our website. This is where everything's going to be except for readings. The readings are inside Icon via files. In terms of those readings, I have a couple chapters from my book as well as from Craig Ender's Missing Data book that refer to maximum likelihood. The textbook for the class, let me tell you about this. It's an Agresti book. I picked it for two reasons. I found it online for $15, and I thought that that was a good deal. And it has R code in it. So because I'm not an R person and several of you are, I thought that would be, that was good. Several of you are. But I'm here all week. I thought that would be nice. I have been reading the book as in preparing this first lecture. I'm going to warn you, it's a little technical. It's a little like, oh, why did I pick this? I'm thinking that the chapters on the models are going to be a little bit easier, but it also is nice to sort of balance out my loosey-goosey way of explaining things with the technical way, because that way when you read things that are more on the technical side, you will have seen it before. That being said, I plan to pretty much go off of only my stuff in terms of what you're going to need to know to do homework and such. It's my lectures, my examples are going to give you everything that you would need to do. So you shouldn't need to rely on the textbooks to do any of that stuff. The other book is this book. I have brought it in case anybody wants to look at it to see if it's worth buying. This is a generalized linear modeling book using Stata instead. So for those of you, I guess that's this corner over here, the Stata people, if you want, do you want to look at it? It's up here. You can look at it if you want. So decide if it's worth spending the money on. It's a good resource, I think, in terms of models and in terms of Stata. So, yeah. So there's that. You can decide if you want to spend the money on that. Otherwise, everything that we will need is going to be right here. I will point out there's 2 class periods right now where we may be kicked out of this room for comprehensive exams. If that happens, we're going to do everything via Zoom. Likewise, if you wake up in the morning and there's snow on the ground, go to your email. If Iowa public schools are closed, my daycare is closed. And that means we will likely be holding class via Zoom. Last spring, remember last spring how fun that was? Yeah, you missed it, Lexi, but yeah. I held class via Zoom 5 classes in a row because every Tuesday, Thursday for like 3 weeks, it was either buried in snow or it was -30 for the high. So if that happens again, we're going to meet via Zoom. I want you all to be safe. I don't take attendance. I trust you guys. We're all grown-ups. If you're not here, I suspect you have a good reason. Do any of you commute from far away to be here? Like more than, I call far away more than 20 minutes. No? Okay. Well then, I was going to say if a commute makes it unsafe for you to come because of weather, don't come. Go via Zoom. Okay? Make yourselves safe. Let's see. Yeah. All right. I have sort of an intro to the class as part of the lecture. That way I wouldn't go too far off the rails. So how about we start there? Does everybody have the course website? If you need to find it in a hurry, remember that I own the Google because my mom spelled Lisa wrong. If you type in L-E-S-A and then Hoffman, you will find my webpage, and then you will find the class webpage from any of those links as well. So there it is. All right, so here we go, my new orange slide color scheme here. This is kind of a mouthful, but introduction to this course and to maximum likelihood estimation of generalized linear models. I know, right? It's a lot of words. I will apologize, but not really, like sorry, not sorry, in advance for packing my slides full of words. The reason that I do that is because I don't want you guys writing down everything I say like a transcriptionist. I want you guys to be able to sit and think and absorb and just have most of what is written down already written down in front of you. So there's a reason why I do it the way that I do it. So this is kind of a mouthful, but this is designed to sort of introduce you to my way of thinking about these things as well as what we're going to cover this semester. So I expect this will take 2 class periods, maybe 3, but we'll just see how it goes. I have never taught this course before. I've taught the material from this course in a bunch of other courses. So I'm trying to put things together in a way that makes sense. I don't know how long things are going to take. So we'll go start and see where it goes. So why are you here? Well, my guess is that because this course is not required, you're here because you really want to learn about generalized models, right?
Yeah.
Yeah, correct. So we're expanding our knowledge of quantitative methods. It's the combination of quantitative data plus the application of statistics to be able to answer questions. Because ultimately, the quantitative techniques, meaning statistical models that you know, are the lens through which you view your research. So think about it this way. If the only stats class you ever took was based on analysis of variance, right? Every research question that you could ever think of would be some kind of group mean difference, because that's the only way you know how to think about it. When you learn new models, you start to see things differently. And those new models hopefully can get you to ask new questions and find new answers. So even if quantitative methods is not your primary field of study, which, okay, this corner excluded, or sorry, not this row, the row behind you, everyone's clustering to data, hopefully knowing more methods will make you better at whatever you came here to do and get you employed. There is that. So this class is going to work like all the other classes. For those of you who don't know me, we're not going to do anxiety. You don't need to be afraid. We're not doing hand calculations. You know why? You're bad at it. Relative to computers, you are always going to be slower, less efficient, and more error prone, because that's human nature. So we're going to let the computers do the calculating. We're also not going to derive formulas or go through proofs. Trust the people whose job that is to have gotten it right. That is just fine. If you're interested in those things, the Agresti book is a little more technical. We'll walk you through some of that stuff. But I don't think it's necessary to focus on that to get you to be able to be fluent with quantitative methods for the purpose of conducting research. We're also not going to be memorizing formulas. It's okay to trust the computer programmers to have implemented those formulas correctly in software. That will be true the very most of the time. We are going to learn new language, new decision guidelines for matching data, questions, and models. So a lot of what we have to learn is going to be logic-based. If this, then that. We've done this so far in the prerequisite material, regression, general linear analysis type models, right? Those models, as we will talk about, are all the same thing because they are built to predict a quantitative outcome with a particular type of distribution. Now, in addition to figuring out what kind of predictors you have and what kind of effects they should have in the model, we have to pick the right model based on the kind of outcome that you're predicting. So it's another level of if, then, if, then. It's all about logic, language, and decision making. How are we going to do this? I don't do tests. I don't think that training you to dump your brain in a room for 4 hours is going to help you. It's never going to be a skill that you need to master in your professional life. So we're not doing midterms, we're not doing finals. I'm not going to ask you to do practice problems that illustrate hand calculations that have nothing to do with research. And I'm going to try to link things together. Even though it's a series of techniques, I'll try to point out when they're related, when they are simple cases of something else, etc., etc. What you are going to do, the same sort of structure that I use in my other courses. It's a combination of what I call formative assessments and take-home homeworks. Formative assessments are going to be administered through ICON. In ICON, they are called quizzes, but they're not quizzes in the traditional sense. They are structured review opportunities. We're going to have one about every other week. The idea is that I'm going to ask you some sort of big picture questions about whatever we covered the previous week that you should be able to answer off the top of your head, more or less. If there's things that you really struggle with, you know that that's something that you need to review. They're probably going to be due on Mondays at by 11:59 p.m. That way I can spend Tuesday morning reading over the answers, seeing if there's any common misconceptions, things I need to go over. We'll go over them in class, and you can have a chance to sort of write down the correct answers. I may circulate answer keys as well as what I think the answers would be, but I'm not going to grade them per se. You get 2 points for doing it. And I know that somehow that might make it less worthwhile, but just keep in mind, this is my version of trying to make you an active learner. Not just sitting there and like rereading through the slides or just watching the videos. It's different if you're doing that looking for a particular piece of information. So a structured review is the purpose behind that. Homework then is going to be the bulk of the class. About every 2 weeks or so we'll have a homework due. They're going to have the same structure for those of you who had me before. It's an online homework system that I've built that I will demo for you on Thursday. It's not active yet. But the idea is that you will have an individual data set that you download. You will have a story, complete with variables, and you will have a series of tasks, questions to be answered, models to be fit, that kind of thing. The answers will be of two types. One is computational, where the answer is a number, and you have to get the number exactly right to usually 2 digits of precision. If you get the number right, the answer turns green. If you get it wrong, it turns red. And you have as many tries as it takes to get it to be green. That way you know that you're on the right track, that you've gotten the software to do what you've asked it to, and that you know what you're asking it for is correct. Once you have all the numbers, the other half of it is going to look like what I would call Mad Libs. Do you guys know that? Like, I know everyone's getting younger and younger and my references are losing, but Mad Libs is like a game where there's fill in the blank where it's like, I need a noun, I need a verb, and then you supply these things without knowing the rest of the story, and then hilarity ensues. That's Mad Libs. Mine are results section Mad Libs, where there's drop-down windows for points of interpretation. So say I ask you for a correlation between variables. The correlation can be positive and significant. It can be positive and non-significant. It can be negative and significant, etc. So there's interpretations that I can test whether or not, hopefully, you have a sense of what the numbers are telling you. But then also the other purpose of them is to be able to give you a template for a results section for a similar technique for what it would look like in a real manuscript. The good news about writing results sections is that they are highly formulaic. There is a standard that everyone tries to follow, and the more boring and formulaic your results section is, the easier it is to understand. It's so formulaic that I literally have written a program to write results sections. That's how formulaic it is. And so I want to give you the keys to that formula so that you can steal it, change what's needed, and use it for your own purposes. So I'm trying to teach you writing without actually teaching you writing. I'm teaching you sort of the building blocks of the writing. These are graded. The green-red computational questions, you know if you got them right away. The other drop-down window questions, you won't know until after you submit the homework. If your answer is correct, it turns green. If it's wrong, it turns red, and the correct answer is given. So that's the way that we're going to do this. And all of the homeworks, again, are very much applied. It's to mimic the type of situation you might be in terms of how to approach a data set, answer a series of questions about it. Okay. With me so far? Questions? Diet Mountain Dew is back, of course. Can't be without it. On that note, I don't have any policies against food or drink in the classroom. If you show up at 2 o'clock and you haven't had lunch yet, please bring it with you. Because there's no good that comes from like sitting here starving, right? That's just not an ideal way to learn statistics, or anything for that matter. So my job, as I said, the textbooks are not your primary reference. They're there to supplement the things that I'm saying or provide it from a different perspective or to a different software package. So my lecture materials and examples should be everything that you need to be able to do your homework. You should not need to ask the Google for any extra help. Everything that I'm giving you should be sufficient. My job is also to answer questions in whatever format you feel is most useful. Emails are fine. If you want to meet with me individually to talk more in depth, that is fine too. And I have group-based office hours, in theory, from 3:15 to 4:30, Tuesdays and Thursdays. I say in theory because if another class gets scheduled, I get booted. But if that happens, I'm going to be just sort of wandering around out there where the computers are. The idea is that if a homework is active, you can come to office hours, sit and work on your homework. If you need help, you raise your hand, I help you, and then you can keep going. And if enough people do that, then I can help multiple people at the same time, and it's more efficient than scheduling an appointment. I'm fine with meeting with people individually, but I will warn you, I'm not the kind of person who hangs out in my office upstairs from 8 to 5. That's not how I roll. I end up on campus maybe 3 days a week, and if I'm here, I'm probably in meetings or teaching. I do most of my real work in my home office. So that is to say, if you wander around hoping to catch me, that's not a good strategy. Send me an email instead and ask when I'm available. And if need be, I can call you on the phone or do Zoom. from my house, so long as you don't mock my pajamas. Deal? Okay. So just because I'm not physically around doesn't mean I'm not around, per se, or available. And they do pay me, right? Like, this job pays me to answer your questions. So don't feel like you're burdening me or otherwise it's a problem, right? They're literally paying me to do this. So your job, ask questions. In class is preferable because this class is not scripted. I have a plan, I have a set of things I've decided to go over, but it's not written in stone. It's not like an episode of Grey's Anatomy where, like, no matter if I pause it or watch it the whole way through, yeah, I know, that one's for you. Like, it's what's gonna happen is gonna happen. Like, no, this class is free flowing. I will change directions, I will stop and review, I will make up shit off the top of my head to try and explain something better if something is broken. So being here or being on Zoom and interacting with me is your chance to be able to guide the way the class goes. So being there is important. Also, if you ask questions in class, then other people can hear your answers. That's also very useful. Reviewing the class material frequently is recommended, focusing on drilling vocabulary, symbols, that kind of thing. But what will help you even more is practicing on data you care about. I'm guessing you guys have a reason to be here, right? These models are going to help you analyze data you care about someday, or maybe even now. Trying to get a hold of a data set if you don't have one already from either a supervisor, someone else in your lab, upperclassmen, whatever, and trying this stuff on that data set will help you. Like I said, textbooks, they're for reference. I'm not wedded to them. And please don't wait till the last minute to start your homework. Homeworks are due by 11:59 p.m. and they have real due dates. Same deal. I'm not trying to be punitive, I'm trying to be practical. Because things with real due dates get done. Things with fluid due dates get pushed. And I'd like to be in the done category. So any assignment that is late is 3 points deducted. Doesn't matter how late. I don't keep track of that. That being said, if you're looking at the syllabus and you see a certain week where you know you're going to be at a conference, or your mom's having surgery and you promise to go there, or you're having comprehensive exams, or whatever is going to interfere, let me know. Send me an email, say, hey, on homework 5, I'm going to be out of town. Can I make it due this day instead? I'm totally fine with that, with working with you. I will never have homeworks due sooner than is currently posted, but they may be due later if we're not done yet. I try to make it so that there is at least a full week between when we finish something and you're expected to be able to do a homework about it. So if we get behind in what I've planned relative to the homework, I will adjust the due dates as need be to make sure that you have enough time to actually get stuff done. In terms of software, I'm trying to make everybody happy, which is pretty much impossible, but this is what I've landed on. We're doing sass, we're doing Stata. M+ is likely to creep in towards the end of the semester for reasons I will explain later, but it's not planned to start right now. One of the questions I've gotten from feedback before, why not SPSS? SPSS is a fine program for what it can do. It's often taught in introductory classes because it is menu-driven. You don't have to actually write code. You can just click your way through boxes. Stata works the same way. It has a very nice menu system to where it will actually generate the code through the windows if you want that. sass does as well, but I've never actually used it that way. It's not as intuitive. The reason that I don't do SPSS is because it doesn't leave us enough room to grow. The analogy that I use is that SPSS is like the hardware section at Walmart versus sass and Stata is like Home Depot. Like, if all you need is a hammer, you can find that anywhere. If you need something complicated and specific, odds are good the 2 aisles at Walmart isn't going to be good enough. And SPSS just doesn't have everything that we need, especially when we get into multivariate models. I can help you in a little bit of R. I'm an R reader, not a writer. Like, I can look at the code and probably tell you what it does, but I couldn't generate it myself. But the Agresti book uses R, and of course the entire internet is full of R code. If you're looking to pick up extra packages, that's one that I would also recommend. Keep in mind that in terms of pragmatics, we're going to be using, if you don't have access to these programs elsewhere, the University of Iowa Virtual Desktop has access to them. you have access for free from anywhere in the world, so long as you're trying to access sass. Stata is only possible to be accessed through the virtual desktop while you are on campus. So if you're deciding which program is going to be most useful, that's something to keep in mind. I know that you can trick Stata access from off campus if you have remote desktop access to a computer here. That's not something you can do on your own computer here unless you have administrator privileges, but it is something you can get someone else to grant you permission to do. Do you know what remote desktop is? Yeah, it's a program on Windows, that's what it's called. I'm guessing Mac has something very similar, where you can log in from anywhere and it will look like you're sitting in front of your work computer. If you run Stata from inside your work computer, then you are on campus. If you're off campus, then it won't work. In terms of focusing on programs, they're a means to an end. That being said, any program that you become proficient with is another line on your CV. If you don't already have one, you should have a technical skills section that lists programming languages you know, like if you know how to write C++ code, or if you know how to build web pages with HTML, if you know any foreign languages, and if you know any stats programs. Those are things that you should be listing as skills. So if you pick up something new, then that will help you get more stuff on your CV. Here's my opinion about sass versus Stata in terms of basic tasks, in case you're deciding between the two. And here's what we're going to do this semester. It's okay if most of these words don't mean anything to you yet. They will eventually. So generalized linear models for univariate and multivariate outcomes is sort of the big picture. We're starting with models for conditionally normal outcomes. This is what's known as general linear models. If you haven't had me before, you know these as specific names like regression, analysis of variance, analysis of covariance, that kind of stuff. We're going to review some of that within this lecture so that you can get a sense of how I'm going to approach this. Then we're switching to the same type of predictive models for different kinds of outcomes. So the simplest case of what an outcome would be if not normally distributed, binary, right? Predicting whether or not something happened. That can't ever be normal, so what do we do instead? Categorical outcomes. Those include ordinal and nominal. Count variables, which are discrete and often have piles of zeros in them. Those fall into a general category. This is my term, if and how much types of outcomes. Like if I gave a survey to you guys, how many cigarettes have you smoked today? Right? The non-smokers would just have a pile of zeros, and then the smokers would have some distribution. There's a lot of variables that look like that. I call them if and how much, and there are models that are designed to fit them very well. And then the last category are continuous outcomes, but they're not normal. And there are specific models for that, and if we have time, I'm hoping to throw in quantile regression, because that's a better way to handle outliers for continuous variables than chucking them or otherwise trying to disrupt the data. So, does that all sound good so far? So all of those models are in the context of univariate models, meaning predicting one outcome at a time. I then want to extend those same models to be multivariate. So the kind of multivariate I'm talking about in this course is different than, say, in a longitudinal course or a cluster data course. This would be things like if you have dyadic data. If you have two persons' responses, like say who are partners, then you want to know like if my predictor relates to my outcome, and if their predictor relates to their outcome, and if my predictor relates to their outcome, and if their predictor relates to my outcome, those particular models are called actor-partner models as one example. We can do stuff like that. Data that come from repeated measures where there's multiple conditions collected from the same person. That's another example of multivariate. And then what I call truly multivariate, which happens whenever you have a series of research questions that are answerable when you have a variable that has to be both a predictor with respect to one question and an outcome with respect to another. The classic example of that is mediation. You've seen the mediation triangle before? Yeah, you'll see it again. It'll show up here. But the idea is that you have a predictor that causes something that in turn causes something else. In that setup, the middle variable is both an outcome with respect to this predictor and in turn a predictor with respect to something else. The only way to properly estimate those models is in a truly multivariate framework. That's what's known as path analysis or mediation analysis. You can shortcut those models by doing each piece separately, but it gets to be clunky and inefficient when it comes to having multiple potential middle variables. This is the point where we may end up having to go to M+. M+ is another program that will be available inside the virtual desktop. It just isn't yet because I haven't requested access for it. So that's the plan. We'll see how much of this we're able to get through. Models for multivariate data and path analysis, in theory, Stata can do it and so can sass. But it doesn't do every combination of things that I want it to be able to do, which is why we may have to move to a different software package. Okay, so with me so far. I'm going to pause, take a sip. Any questions? Yes, please.
Hypothetical question. You were talking about the actor, what's that called? The dynamic?
Actor partner. I call it this model because that's what the paths are always drawn with.
So, just hypothetically, what if you have like a child that you're trying to predict the outcome from and you have two parents talking about the child? Would that be one of those?
Do the parents also have outcomes?
Yeah.
Then yes. Then it would be like a triad sort of thing. Like dads predicts moms and moms predicts moms and kid predicts moms and like all, that. That's a multivariate model. Those models can be done fairly straightforwardly in univariate software unless you want to have one outcome predict another. Like if the line is like, I have these predictors and I have these outcomes and the outcomes are related, but not like one causes the other in terms of the theory, you can do that in regular software. It's if a variable has to be both a predictor and an outcome simultaneously, that's where the problem shows up. The actor-partner models typically do not have that characteristic. Does that help? Okay, yes. I have examples for those already that I could point you to from other classes, but haven't got those for this yet, but it's coming. Okay, good. Anyone else been wondering if this is going to work for that? In their heads, they're not yet? Fair enough. We'll get there. So the big picture. I want to spend a little bit of time giving you my worldview and why I think this class is so important. Because I do. I wouldn't make a new class if I didn't think it were important. And other people might not agree with me, but I want to give you my pitch for why you should come back on Thursday. And keep coming back, right? It boils down to Legos. Legos, children's blocks. If you understand the elemental building blocks of statistical models, then you can build anything. That's the premise. So I want to describe to you what the 4 blocks are that you need to do probably 99% of all statistical models and how those things are going to be approached in this course. Because we're going to start here with a mess. We're going to get over here to something pretty cool. So where did this come about? My first job was at the University of Nebraska-Lincoln as a professor. And I tell you this because I did all of my undergraduate training in psychology there as well. So they had an exceptional amount of coursework in research methods and analysis at the undergraduate level. There were 3 courses, and then I stuck around in my senior year of undergrad. I did all the grad courses too. And they were all taught from sort of I would call an old school perspective. Sums of squares and ANOVA this, and we have this technique and this one and this one and this one, and they're not connected in any sort of way. And so I got used to sort of those ideas. But then when I went to graduate school and I tried to learn new things, I didn't understand how what I knew before was related to what I was doing then. Just as one example, did you know that error is variance? I mean, that sounds simple, but it was like earth-shattering to me to figure this out my first year of graduate school, because there's sums of squares error, right? Error means you messed up your experiment, right? Why are people from the same condition different? That's error. That's bad. And then there was regression. No, I have variance in y, and I'm going to have r squared for how much variance I accounted for, and individual differences, right? Isn't that a nice way to say variance? And then I was like, wait a minute. I don't know why there's individual differences. That's error. Error is variance. And being able to just link those two ideas unified a whole lot of things that I had thought were somehow separate and different. And then when I was hired back to Nebraska, it was such a fluke, honestly, because there was one person who taught all my classes and had been doing it since 1985. And it was the year that I was on the market. It was 2006. They finally had a job for another quant person. And I happened to take it because my family was from Nebraska. And it was like the stars were aligning. And so now all of a sudden, I think it was, I'm trying to do the math in my head, 11 years after I left, as an undergrad, I was back as a professor to pick up where my classes as an undergrad left off. Because that was my job. They were like, can you just teach anything? We don't have any advanced anything. And they were like, we want multi-level, we want SEM, we want all this stuff. Okay, I did that. And what I found was that there was this ginormous canyon between the sums of squares type classes and the world of multi-level and structural equation modeling. I was having to teach like 8,000 new concepts at the same time. And the trick is that many of those concepts weren't actually new. They were things that were in the sums of squared old classes, just not said that way. And so it made it way harder to teach the advanced materials because they didn't understand how they connected to the stuff they already knew. So when I taught those classes for a number of years, and then not coincidentally, they hired another quant person, Jonathan Templin. And the first semester there, we team taught a new class. We called it the bridge course informally because it was supposed to be the bridge between sort of the old school sums of squares and all the advanced stuff that people were increasingly needing to know. And that course, the first time it was offered, had 46 people in it. It was like this huge room, and the two of us literally team taught it. So it was sort of fun to like riff off of us because we each had such different styles. But that same idea is what I'm trying to bring into this course. It's what are the building blocks you already have? What are the building blocks you need to not only be able to do all the stuff I just talked about, but be able to grow into the advanced courses if that's what you want to do. And I'm here to tell you that's what you want to do. So it's a Lego-based philosophy for what goes into quantitative methods and models. There's only 4. Linear models, estimation, link functions, and that's what we're covering this semester, broadly construed. These are the building blocks. Everything that we're going to cover is a specific instantiation of this combination of ideas. If you understand these 3 things, that's going to make the advanced courses, so to speak, the ones with random effects or latent variables, much more palatable. So for some of you, this is going backwards, right? So I see several friendly faces from clustered multi-level models or longitudinal models. And guess what? This fall, I'm taking over SEM from Steve Benbar. So all of this stuff that you're learning now would really have been helpful to learn this stuff. Because when I have to teach courses with random effects or latent variables, and by the way, the reason that there's not 5 blocks is because these are the same thing. That's another really important point to grab. All of this stuff doesn't have to be new. When I taught these things at Nebraska my first time, this entire page was new in one course at the same time, and it was really much harder than it needed to be. So what do I mean by linear models? They rule the world. They're the mechanism by which all research questions are going to be answered. And so when I say things like, is there an effect of this variable? Is the effect the same for everyone? Is the effect still there after considering something else? Those are the kinds of questions that linear models are designed to answer. It's the logical process by which you build predictors and specify what kind of effects they have in the model. So for instance, is there an effect? That's just a bivariate question, right? Does X relate to Y? Is the effect the same for everybody? Can you think of a stats term that goes with that idea? Does the effect of X on Y depend on some other variable? An interaction, and a synonym for interaction, fancy word starts with M. Moderation, yeah. Yeah, so being able to understand that that concept goes with interaction term. Likewise, is the effect still there after considering something else? That's the idea of regression, right? Any kind of linear model where you're putting in multiple predictors to compete against each other and see who's still standing after you take into account their joint relationship and their unique relationships. So the idea of how to recognize that common element, no matter what you're doing, is really important. So a linear model's worldview, the way that I want to approach this, starts with traditional models taught from a different perspective. Those of you who've had me before know this way. For those of you who haven't, this is why I wanted to make sure that we review it. So the most intuitive way to present this is in what people would call linear regression. Courses taught on linear regression focus on what the regression model equation looks like. Those models, terms, show up directly on your output. And there's a one-to-one correspondence there that's very comforting and specific. That same thing doesn't get taught that same way in analysis of variance courses. For whatever reason, it's focused on boxes of here's this grouping variable, and here's the mean for this group, and the mean for that group, and the mean for that group. And now I'm going to have an F test that tells me if those means are different, and then I'm going to have another F test that tells me if the differences in the mean are different, and it's like there's just these boxes and T's and F's. And the model that goes underneath it is usually not even taught. So that puts you into a world of hurt when you need to combine models that have grouping variables and regression type models. They're all the same thing, and that's the way that I teach it in the introductory course that I just finished with. So to review, a one-slope general linear model example. If I don't know anything else for a person, that idea is conveyed by what's known as an empty model. Empty means no predictors. This is a model you probably haven't seen before if you haven't taken a multi-level modeling class, because there's no real reason to fit it, but it's very useful conceptually. If I have a model like this, where Y for each individual is my outcome, let's say that I'm trying to predict income. Those of you from 6242 may recognize this slide. If I don't know anything else about a person, what is my best guess for what their income is going to be? I have no predictive information whatsoever, and I got to make a decision for Y sub I, for you. What's my best guess as to what your income is going to be? Yeah, the mean, right? The mean is the most likely value by definition. That has to be your best guess. So in this plot, the y-axis is my income. This straight line here shows what the empty model predicts. Now it's a line across education, which is coming up in a second, but it conveys the idea that everybody has the same predicted y. And the difference between each actual dot here and the prediction, that's E. That's the idea of a model residual, how far off your predicted outcome is from the real one. So let's say for this person out here, focusing on them, they're way up here. So we way underestimated their income. So they have a residual of 115. They're off by 115. But we don't care about each person's residual specifically. What do we care about?
Overall variance.
Overall, the collection of residuals and how much residual information there is. So this model, how far off each observation, y sub I, the real one, minus the one that is predicted for you, this y with a little hat over it, y hat means y predicted. This model predicts only from the mean, but y predicted is an idea that translates. This returns all the variance in the variable. This literally is the formula for variance. It's how far off each observation is from the mean squared, sum them up, and divide by n minus 1. Now, why is it n minus 1 and not n? Do you remember that? And don't say sample versus population. I don't want to hear that.
Because of the intercept.
Because of the intercept. Keep talking.
So you know the intercept, so it's one of the, I don't remember, but it's n minus 1 because the 1 is the intercept.
Yeah.
if you had more, if you had more predictors, it'd be a minus whatever.
Yeah, so the general term, degrees of freedom, number of things that you could estimate to describe your outcome. If you wanted to, you don't need a model at all. You could have, let's say this is 100 people, for example, you could have 100 parameters. I could have the U parameter and the U parameter and the U and the U and the U and the U, and I give one to each of you. That will perfectly describe income. It's stupid and useless, but it would be perfect. So somewhere between stupid and useless, just recreate the data and find something to summarize and predict the data. We're on the latter camp, summarize and predict. So we already had to find a mean in order to find the variance. That's why it's -1. So whatever points that we've spent towards prediction get taken away from us in this idea. This is a description of ordinary least squares estimation. That is a term that describes how do we know what beta 0 should be, the intercept. Why is it 40? Because that is the value that minimizes the sum of squared errors. It is a mathematical formula that someone else figured out. You can trust them that it's right. But the reason that 40 is the best answer is because it minimizes this term in the numerator. That's where it came from. If we add something to the model, let's add education as a predictor. Education should be related to income, right? That must be one of the reasons you're here, right? More education, more money, up to a point. Yeah, thank you for giggling at that. It's true. It depends on your perspective. So if I add this to the model here, now beta 0 is my intercept, but it's not 40 anymore, it's 27. It changes its meaning. So that's one idea of like understanding linear models, is understanding conditionality. Beta 0 at 40 was unconditional before. It's the best guess for everybody. Beta 0 now is conditional at 27 because what kind of person, their best guess is 27. For what kind of person? Person with what?
Okay, school education.
High school education, and that is correct because of the -12. Now, why did I do that? Why did I center, as this is called, education so that 0 means 12 years? Yeah, education 0 would be an intercept of somebody who never even went to grade school. I don't want to predict some income for someone like that. I centered it so that the intercept stays meaningful. And if I have interaction terms, test moderation, the interacting predictor effects would stay meaningful as well. So this centering idea, that's staying with us. The slope estimate that minimized the sum of squared errors worked out to be 6.6. This person in particular that I'm predicting for had an education value of 8. Does that mean that they only went to 8th grade?
Means they went to 8 additional years of
Yeah,
school.
they went to 20th grade, whatever that is. And yes, and that's part of the reason why they're up here in terms of income. So now my best guess idea is conditional. It depends on what value of x you have. And the difference between the naive guess, the mean for everybody, and my new guess is better. So that red part, that's explained. Why is it that this person has a higher income than the mean? Well, part of it is because they went to 20th grade. But is that all of the story?
No.
Nope. This much unexplained left. They are still making way more money than education alone would suggest. There's something else out there. So this variability then, the same idea, where you are for real, your real outcome minus what is predicted, where what is predicted has changed, but it's still the same idea of y hat for what is predicted, minus n minus 2 on the bottom, because now to get that sums of squares, we spent another point. We had to estimate the slope too. And the variability that we have after accounting for education is down to 1594 from 1980. Would I do something with that information usually? The difference between them? Yeah, that's the idea of R square. or what proportion of the original variation, 1980, is explained. And that would summarize how well our model did in terms of prediction. We only spent 2 points, and we reduced the amount of error or unknown reasons for individual differences, whatever you want to call it. So linear models, more generally, that idea can be extended to include multiple kinds of predictors and multiple slopes. So to match the notation in the Agresti book, I'm going with P as the number of fixed effects. So we're starting with the intercept 0 here, and then the first predictor x1, the second predictor x2, all the way up to xp as the last term. Why don't my beta 0, beta 1, beta 2, etc. have eyes? They're constants, which means they apply to everybody. That is one of the main differences between this class and the class before it and the world of multi-level models or models with random effects, in which case the betas pick up eyes. Because students can have different kinds of effects, say across teachers or across classrooms or things like that. The difference between the first equation, that's for the original outcome. The second equation lumps off the E, and it just talks about what is predicted. So the difference here, all of these things, the difference in Y for 1 unit difference in X, all of those are interpreted the same way. I will note that this GLM in the Agresti book stands for generalized linear models, not general. General is one specific subtype. We'll get to that in a second. So more generally, how do you know what to do with these slopes, what they actually mean? How many slopes you need is the first question. One slope is sufficient if you're trying to capture the mean difference between a variable that only has 2 categories. There's only one possible difference. Going from category 1 to category 2, that one slope covers that change, you're good. The same is true if you have a nonlinear trend that is captured by one term. So for instance, if I take the log of a continuous predictor, that creates a curve regression slope instead of a straight one, but it's still only one slope. You may need more than one slope for one predictor if the predictor is quantitative and you're trying to capture nonlinear effects. So going back to the picture here, do you think that income improving by the same amount for every difference in education is reasonable? Probably not. Education is sort of a stepwise phenomenon, right? You got high school, and then college degree, and then graduate degree, right? If you only get through 13th grade, that's not going to help your cause. So if I wanted to say, what is the difference in income as a function of that sort of stage-wise approach? There's one slope that describes the effect of education up until you graduate high school, another slope that describes the difference between, say, high school and college, and then maybe graduate school, something like that. Then even though education is one predictor, it would take multiple slopes to convey the idea that different ranges of the variable have different slopes. That is what's known as a piecewise model or a linear spline model. That gets taught explicitly in longitudinal analysis as one way to model the changes over time, but that same idea, linear models background, applies to any kind of quantitative predictor. Same thing if you want your line to be curvy in a quadratic function. That takes 2 slopes instead of 1. So going back to this linear models idea, it's not always clear if each of these terms is a separate predictor or parts of the same predictor that describe different aspects of it. So a quantitative continuous type variable that has a nonlinear effect is one example of when it takes multiple slopes to convey its effect. Another is when the variable is categorical, it's a grouping variable, and it has more than 2 groups. If I have 3 groups, I need 2 slopes to differentiate the 3 groups. If I have 4 groups, I need 3 slopes. In general, it's C minus 1 slopes is needed to differentiate C groups, And the reason that it's minus 1 is because the intercept is there instead. Even though the model only provides certain group differences, you can get the others as linear combinations. And that's the part of ANOVA that isn't often taught that I think should be. Why is this all under the word general linear model or generalized linear? It's referring to a linear model equation that looks like this. Slope times variable plus slope times variable. That's what linear means in this context. Even including a quadratic term, like if one of the predictors is x squared, it's still a linear model because then it's slope times x plus slope times x squared. That is nonlinear in the variables specifically. It's still a linear model. When would you see a nonlinear model? Something like this instead. This example is what's known as an exponential model, not just log transforming something to sort of cheat it, but a real one. It has 3 parameters. It has some kind of either an intercept or an asymptote. It has a rate of change, and then that rate of change is multiplied by e to the variable times an actual parameter that's called rate. So this beta 1 times e to the something violates this slope plus times variable format. So this is a non-linear model. What we're doing is linear. They're all going to look like this. Slope times variable plus slope times variable. All fixed effects are characterized by these pieces of information. The estimate that's the best guess, a standard error that indexes imprecision, is supposed to be the average distance of the slope from the population slope. You take the estimate and divide by the standard error. That ratio is either going to be called t or z, depending on your software. It's compared to either a t or z distribution to give you a p-value that tells you the probability that the effect would be observed if the true effect is actually 0. And you can use that information to convey a confidence interval. So this is one of the first things that is going to be different depending on which software program we use and which type of model we use. Sometimes it may be called t and sometimes it may be called z. Here's why. It boils down to whether or not we're worrying about denominator degrees of freedom. We're worrying about the number of possible parameters we could have used to predict it and how many are left over, or whether we're like, doesn't matter. Generalized linear models often do not have denominator degrees of freedom. So they show up as z's. That's true in M+ software. It's also true in a bunch of the different Stata modules. It's not true in sass or SPSS, which still tries to use denominator degrees of freedom. If you're testing one slope at a time, you're either going to get a t or a z back. If you're testing a set of slopes together, you're either going to get an f or a chi-square, where f times the number of slopes that you've tested is chi-squared. The latter is another concept that shows up all the time in sums of squares land that isn't taught that way. But I guarantee you know what I'm talking about. So here's just a reminder on where standard errors come from. They come from the residual variability. Standard errors are calculated in sums of squares land. They will have to be estimated otherwise. But the multivariate wall test thing. Here's the first example that you would have seen not phrased this way. Testing whether or not the variability explained by the model, the set of predictors as a whole, is significant. Whether or not r² is greater than 0. That F test that shows up, it's called like a ANOVA test on your output, that is a multivariate wall test. It is one specific example of a general concept that you can test a group of slopes at a time to see if jointly they do something. So in this particular case, in sums of squares land, you can calculate it by hand if you're in the world of general linear models. The F at the end of the day is the same thing no matter what though. It's a ratio of information that you know over information that you don't. Each of these is weighted by how many terms it took to know it. So all things being equal, known would count less if you had to spend a lot of slopes to get there. But because it's known over unknown, the worst that f should be in theory is 1. Like you put in something that didn't help you at all. You don't know any more than you started with. I have seen f's under 1, but it's pretty rare. So that's one type of f test that you would have learned in sort of sums of squares land. Another is the idea for a categorical predictor like in ANOVA. Let's say that I have a 3-group variable crossed with another 3-group variable. That means that variable A with 3 groups needs how many slopes to differentiate those groups? 2. Variable B with 3 groups needs 2. If I want to fit the interaction term between them, how many slopes do I need to fit the interaction? It's 2. And so that's a linear model's perspective. You don't see it that way because all you're seeing is like the 3x3 grid of the cell means. And those 6 slopes will give you everything that you need. Hang on, my math is off. There's 9 cells. There's 1 intercept. 1, 2, 3, 4, 5, 6, 7. I'm off. I shouldn't make up shit off the top of my head. That's the moral of the story. I'm very bad at it. But more than 1 is the idea. That's the idea. That's what I'm going for. I'll return to that later and get it right, I promise. But if you want to say, does variable A have an effect? Right? No one slope answers that question. You have to test the set of them. The same question with variable B. Does it have an effect? I don't know. I got to test the set of them. So the omnibus mean effect. That's a special case of the multivariate Wald test. Those of you who had correlation and regression, did you do hierarchical regression at any point? Stepwise regression? Like a set of stuff and then you add another set of stuff? Okay, that test of whether the new set of stuff improved R square, whether that change in R square is significant, that's this too. That F test is the same idea. It's whether the chunk of slopes that you added helps the model. So being able to phrase hypotheses this way more generally, are you testing one thing? Are you testing more than one thing? That concept transcends all the different kinds of models. So this is a new slide that I developed that I'm bringing into the intro class that I think might help simplify things. Once you figure out how many slopes that you need and how to test them, you got to put some words on that. This is where linear models are really, really important because it's real easy to look at a number and not know what it means. Real easy. sass, SPSS, data, they'll all be happy to give you the numbers. It does not have an additional column on the output that says what it means though, although it could because it's highly formulaic. Once upon a time, Jonathan wanted to write a software program that did like all analyses, and to help it sell, I volunteered to write the code that would add that column. Like, can you imagine how much a package would kill if the interpretation showed up on the output with it? Like, I'd be out of a job. So that would be a bad idea. Maybe in my retirement or something as my final to the world, right? You don't need me anymore? Fine. I'm going to put all the data analysts out of business. But no, it boils down to very simple taxonomies. There's 3 kinds of slopes. There's bivariate marginal, unique marginal, or unique conditional. So what do these mean? If I have a model that has one fixed slope, does X predict Y? The end. And that slope, one slope for the variable, that slope is a bivariate relationship, meaning it doesn't control for anything else, and then it has to be marginal. It is the slope for everyone. How X relates to Y? One number. If I have a model with more than one slope in it, now that could be more than one slope for the same predictor, or it could be more than one slope because more than one predictor. Doesn't change the interpretation. Each of the slope's main effects is called unique. It's the effect of that particular term controlling for everything else. So when you do dummy coding in regression, right? Like if I have 3 groups and I have one dummy code that gives me the control group versus another, and the control group versus the third, right? That's a way to put it in. Those things only mean what you're intending them to when they're together because of this principle of unique effects. Otherwise, if I have control group versus the other, control gets a 0, other gets 1, the other group over here gets a 0. It's lumping together the two in a way that you didn't intend. Unique is what fixes it. Same thing if I have theory A predicts that this predictor is really important, but theory B says it's that one. Who wins? Put them in the same model, let them fight it out. It gets harder to tell who wins the more related the predictors are in the model, but you can still tell. So that's the idea of unique, that the interpretation is different than it would be if it were all by itself. If the predictor that has the slope is not part of an interaction term, then the unique effect is marginal. It applies to everyone. If the predictor that has the unique effect is part of an interaction, it's conditional. Not only is it the slope controlling for all the other stuff, it's the slope that's specific to the interacting variables being 0, conditional, in the same way that the intercept is specific to when the predictors are 0, conditional. Let's practice. Okay, here's an equation for you. I got 3 predictors, F, G, and H. They each have main effects. G and H also have an interaction. So which term would I use to describe the effect of F in this model? Bivariate marginal, unique marginal, or unique conditional? So it can't be bivariate because there's too much stuff here, right? So bivariate is only when there's one thing. So it's unique. It's unique marginal because beta 1 is the effect of F, period. No matter what. So the effect of F is given by, for those of you who are typing in something here in Office, Alt equal is how you open the equation editor if you want to write real equations. You can type a Greek letter like beta by putting a slash, it's the one that's above enter, and then typing the word and hitting the space, and it jumps into the symbol. Yeah, it saves a lot of time. Subscripts is shift and then underscore. It's the one next to the 0. So if I do that and then I hit the space, it jumps in like that. So beta 1 is the effect of F, period. It's unique because it's the effect of F after controlling for G, H in the interaction, but it's marginal for everyone. G, which is this. Oh, we got disagreement here. I heard unique. That's true. Now G shows up here, and it shows up here. This is conditional. Unique conditional. That means if I wanted to describe how to get the effect of G for anybody, I can't just use beta 2, right? Yeah, so we're going to do the trick. Remember the trick? I know it's been at least a month, maybe more, but we're going to do it. So here's the stuff that's relevant. First step, find everything that has G in it and G only. So do I need beta 2G? Do I need beta 3H? Oh, bye-bye. Do I need beta 4? Yep. Okay, second step. Take the G out. Take this G, go over here, take this G, put it back here. Now I'm going to throw some brackets to make my order of operations correct. There. How do I get the slope for G to describe what it would be for any kind of person? It's beta 2 plus beta 4 times H. that means that beta 2 is only the slope for G when what is true? What is this? When this goes to 0. So putting that together, that means what beta 2 is. You can't just say, oh, beta 2 is the effect of G. That's wrong. A lot of people would be tempted to say it, but they would be wrong. That is the effect of G specifically for people with an H of 0. Did I screw something up?
I wonder if the first one you need to put FI different than the first, the unique marginal
Unique marginal.
one. Do you need to put F1 there? FI there?
It's the effect of F, so it's like I'm taking it out. But yeah, if you wanted to make it like.
So then for the second one, would you take G out or you keep?
Yeah, so it's like the effect of G would be like just the term that multiplies it.
Oh,
So I wanted to keep it there to show like where it went, but yeah, at this point it's gone. Like the effect of G is that, the effect of F is this. Yeah. So this is an important concept right here. Because what this means is that there is an infinite number of possible G slopes given by the model. It depends on H. So is G important? I don't know, depends on H. Is G significant? I don't know, depends on H. So the G slope that's given to you in your output is only one of the possible G slopes. And you have to know how to get another one. Do you remember how to get another one? How do I make the software do that for me, do math for me? We practiced the hell out of this, I know you know. This is our friend estimate statement in sass, test statement in SPSS, lincom in stata. This is one of the things that you do not get taught in sums of squares land that you need to, because this is a really important skill to be able to do a linear combination of slopes or intercepts as need be. So if this is something that you haven't been taught before, or you got taught it and you want to see it again because you need some practice, either way, no judgments, I have posted last semester's version of 6242. It's weeks 12 through 16, where we reviewed how to get linear combinations out of fixed effects in the context of slopes and interactions. The same would be true for categorical variables to get the difference between groups that's not directly given by the model. It's one group minus the other. So you can review that material there. And that will help you because we're going to do all the same stuff this semester. But not today, because we're done. I'm getting better at not running over my time. So we'll pick up where this left off then last time. So, all right, questions before we adjourn? Okay, then hopefully I will see you Thursday. I haven't finished my sales pitch, but I'm getting there, I swear.